till now we have seen only single component at a time, either L, C or R, but single component at a time. Now we are seeing a joint of these components, AC voltage applied to a series LCR circuit. So here this R, this C and L are in series because they are directly connected, they are in series and they are connected to AC power source. So now we have to understand what will happen when we connect this LCR circuit in series to a AC power source. So let us understand this. So in this figure, this is shown. Again, we know voltage is equal to Vm sine omega t. Voltage is a sine function. Now, if Q is charge on the capacitor, we assume that Q is the charge on the capacitor. I is the current and I is the current in this circuit. Since this is a series circuit, so current in all the elements will remain I. Current must remain same in a series circuit. From Kirchhoff's law, what we know, this voltage drop, this voltage generated at this point must be equal to voltage dropped at this first point, second point and third point. So what we are doing, so previously we have just put only single element, now we have to put all the elements. So voltage dropped across this resistor is IR. So first voltage dropped across this IR, that means resistance. Then voltage drop across this capacitor is Q by C. Then third voltage drop across this inductance is LdI by dt. So we have combined all three voltages drop and this must be equal to voltage given by the source. So source is providing the voltage and these are dropping the voltage. So this V is equal to LdI by dt, this first, this second, this third. So this is a positive, this is only a summation, so we can write in any order. So IR plus Q by C plus LdI by dt. So in this form we have written. Now what we need? We want to determine the instantaneous current and its phase relationship with the alternative voltage. So as previously done, we need to determine what is the current, how the current is changing and what is the difference between voltage and current, that means what is the phase. So we will solve this problem by two methods. First technique is the phasor technique, we have learned about phasors, and in the second method we will use analytical techniques, that means we use mathematical techniques to solve this problem and we will get the time dependence of I. So what is the meaning of time dependence? A formula where I is changing with time. So here this is time dependent V. So here it is time. So this gives us how voltage is changing with time. Previously we have solved that how I was changing with time. For one case of resistor we got this I is equal to Im sine omega of t. So this is time dependence of current, this was for resistance. So this is time dependence, that means it is also sine wave and in phase with the voltage, but in capacitor or inductor this was not true. Now let us use the first technique, phasor diagram solution. First we are solving it with phasor diagrams, then we will solve it with mathematical methods. So now from the circuit shown in this figure 7.12 that we have seen, that has one L, another C and third R. So we see R, I and capacitor all are in series. Therefore current in each element is same. So we know current remains same in AC circuits having the same amplitude and phase. So let us assume that this current is Im sine omega t plus phi. So what is important? Current in each element, whether that is R, C or L, current must be same in all the elements. Current is I and I is equal to some current I max sine of omega t. But what we are more interested in determining this phase. What is the phase of this current with the voltage? That is more important to us, because sine omega t we understand, but what is this phi? So that we want to know. But one thing is clear, since this is a series circuit, the current will remain same in all the elements, but we are interested in this phi. Phi is the phase difference between voltage and the source and the current in the circuit. So what is phi? We have previously seen that suppose this is current and this is voltage. So this voltage starts initially, this current is peaks at after some time, so there is some phase difference phi, and in this case it is pi by 2. So current lags voltage by pi by 2. But we have to see what is the phase difference phi is here, because it is not that simple. Here we don't have a single element, we have 3 elements that are in series. Now we will use our previous knowledge that we have learned till now. So let us make a combined diagram for this complex case. First we have considered that this I be the phasor representing the current. So since we know there is only one current, I is equal to Im sine omega t plus phi. So current is same because circuit is in series. That's why we have taken only one phasor for current. So this is phasor for the current. This is I. Further, VL, VR and VC and V represent the voltage across the inductor, resistor, capacitor and the source. So we have seen, or we have taken this VL is voltage across the inductor, because L. Voltage across the resistor is VR, voltage across the capacitor is VC, and V is voltage across the source. Now previously we have seen that in case of resistor there is no phase. Phi is 0 between current and voltage. So VR is parallel to I. So this voltage is parallel to I for case of VR. Both voltage and current are in phase for a resistive element. So what we are doing? We have taken current with a single phasor because current flowing in all the elements is same. So current is in this direction and we are changing the direction of voltage phasor. So voltage phasor for resistance is in the same direction as the current. Now what is the direction for other two? Now we know voltage phasor for capacitance is pi by 2 behind. So what we have learned in case of capacitance, that current is pi by 2 ahead, and we have learned that ahead is anti-clockwise and lag is clockwise. So voltage and current, so current in a capacitor is pi by 2 ahead, or we can say voltage is pi by 2 behind. So we can say any of these, that current is ahead or voltage is behind. So behind is clockwise. So voltage is 90 degree angle or 90 degree behind in case of capacitor. So VC we have shown 90 degree on the clockwise side. Now in case of inductance I and VL is pi by 2 ahead of I. So in case of inductor, what happens? This VL is pi by 2 ahead. And how do we show ahead? Ahead by anti-clockwise. So for inductor, this voltage is ahead of current. So please remember, previously we have studied current is lagging or current is ahead. But here we are showing it in terms of voltage. So things will just reversed. So in case of inductor, voltage is ahead or current is lagging. Current lags or voltage is ahead, both are same thing. In case of capacitor, current is ahead or voltage is lagging, both are same thing. So we have got this kind of complex phasor diagram. Now let us see what are the lengths of these VR, VC and VL. So we know VRM. So maximum voltage drop across resistance is Im into R. VCM, maximum voltage drop across this capacitance is Im XC, where XC is capacitive reactance, and maximum voltage drop across inductor is Im XL, where XL is inductive reactance. Why the magnitude is equal to maximum? Because in the phasor diagram we have learned this length of maximum voltage on one side, either side, is taken as the length of the phasor.